The regular languages correspond to a class of problems for which very useful formal tools exist. And so it's really nice to be able to answer the question, I've got a problem, is it one of these? If it is, you can show that it is by solving it using one of these tools. So that's easy. The question often arises, though, what's this boundary? Do I have a problem that's outside it and I should quit trying to shoehorn it in? So how do I show that there isn't one of these things? And the answer is we have a result that helps us. Here's the pumping theorem for regular language. And it tells us a property that every regular language has. So it's stated like this. If L is regular, then this property, and the property is that every long string in the language is pumpable. Now, I haven't told you what long string means, nor have I told you what pumpable means, but just let's look at the structure of this thing. It says that if the language is regular, then for all x, if it's a long string that's in the language, then it is in fact pumpable. Now, stated like this, this isn't very useful, because if the language is regular, and we already know that, then we don't need to care about pumpability. What is really useful is the contrapositive, which remember follows. The contrapositive says, well, if it's not true, all of this stuff, then it's not true that the language is regular. So if we could establish this, we would know that we're not dealing with one of these languages, and we should quit trying to make it work. All right, so how do we do that? Well, before we can get very much farther, I have to tell you what long and pumpable mean. So let's write that out in our logical notation. So if L is regular, every long string is pumpable. So let's write it down. If L is regular, then there exists a k that's greater than or equal to 1, such that all strings whose length is greater than or equal to k, that's what long means, have the property that there exists a way to carve the string, we're calling the string W, carve it up into 3 parts. Let's label them x, y, and z. The x, y part together have to occur in the first k characters. Think of it as y has to come near the beginning. Y is the piece we're going to focus on, and it cannot be the empty string. The part you label y has to have some text in it. And furthermore, for every q, if you put q copies of y in place of the original y, then the result is a string that is still in the language. You can pump these copies of y out or in and still get a string in the language. That's the claim. Now, even if you don't quite get what's going on with strings in the language, you can still see what the structure of this is. And we ought to be able to apply what we know about logic to transform it into a way that we'll be able to use. So in particular, this is the original form. If L is regular, then every long string is pumpable. Remember, we want to use the contrapositive. If L is regular, then this. The contrapositive says the not of all of that implies not regular. So there we go. Can we use that for anything useful? And the problem is, of course, that in this current form, that's hard. We've got a negation on the outside of the whole expression. And when we actually look at strings and languages, we're going to be able to answer questions about particular strings and the language. And we need to be able to evaluate those, not some quantified expression way out here. So let's see if we can use quantifier exchange, maybe some other things, to try to get this into a more usable form. So we can push the not. We'll call that formally quantifier exchange. We'll get rid of the not here. The existential becomes a universal. And the not goes there. Good. Except now we have a not in front of this universal. So it goes away. The universal becomes an existential, and the not goes here. And now we have another not in front of an existential. It goes away. This becomes a universal, and the not now goes in front of this whole expression. All right, now we'd like to continue to push the not through. Now we don't need quantifier exchange. What we need is De Morgan. This is an and, so we have this and this and this and this. So we push the not through by negating this one, this one, this one, this one, and the and becomes an or. So now it's got to be the case that at least one of these things is false. And we have one last quantifier exchange. All right, so if we can prove this, then we can prove that our language isn't regular. Let's look at that in a slightly neater way. Here's what we produced. Now we can show, if we can show that for any k, and just call it k, that there exists a string w such that for any way of carving it up into x, y, and z, at least one of these things is false. Well, let's only consider the ways that meet these first three. In other words, we carve it up. The part we're going to call y has to occur relatively early in the string, and the part we're going to call y has to have some characters in it. We consider only x, y's, and z's that meet those requirements. That means that this one is going to have to be the case. That means that there exists some q such that this is false. And so how do I use this theorem? I use this theorem by saying, well, if this is true, this asserts that there exists a string, fine. All I have to do is find one. Having chosen my w, whatever I'm going to claim has to be true for all x, y, and z. I don't get to pick. I have to try all logical possibilities. For each of them, I have to show that this is true, namely that there exists some q. I get to pick w. I get to pick q. I don't get to pick y. But if I can, using that logic, show that this entire thing is true, then I have a proof that L isn't regular. Note that to understand this theorem, what we need is some understanding of what's going on in here if we really want to use it. But we can understand the reasoning that we used and why the theorem looks like this just by applying what we know about quantifier exchange. And when we look at this, let's just make one last observation. Why does it seem hard to use this theorem? Note that we've actually got 6 nested quantifiers. For all k, there exists a w such that for all x, and for all y, and for all z, there exists a q. The logic is straightforward, but sometimes hard for people to get right.